Welcome to This Explainer. Today, we're taking those simple, everyday actions we all do without a second thought, and we're going to reveal the fascinating and honestly sometimes totally surprising scientific rules that govern them. You know, we throw around words like work, energy, and power all the time in casual conversation, but in the realm of science, these terms have incredibly precise mathematical meanings that literally shape everything around us.
Okay, so let's dive right in. Picture a classic playground scene. Now, put on your physics glasses for a second and ask yourself, what actually determines the speed of a kid when they finally hit the bottom of that blue slide? Like, will two kids of totally different sizes reach the bottom going the exact same speed? Is it about how steep the slide is, the height, or is there something totally invisible at play here? Well, we're going to uncover those answers by following this quick 6-step roadmap. We'll look at the science of work, positive, negative, and zero work, the work-energy theorem, forms of stored energy, the power of speed, and finally, the dark energy mystery. All right, Section 1, the science of work. Right off the bat, we need to completely challenge what you might think working hard really means in a scientific context. So here's the crucial point. In science, work isn't just about effort or sweating or being exhausted. It has a strict definition. It's a constant force applied to an object, multiplied by the displacement of that object, and here's the kicker, in the exact direction of the force. Think about lifting a 5-kilogram bag of meat. To lift it slowly by 1 meter, you have to apply an upward force to overcome gravity, right? That is work. But check this out. This is the tricky part. If you carry that heavy bag, holding it up against gravity, but you walk steadily forward across the room, scientifically, you are technically doing zero forward work on that bag. I know, it sounds crazy, but the force you're applying is vertical, and the displacement is horizontal. They just don't match up. Now, if you lift 3 of those bags to the exact same height, you need 3 times the upward force, meaning you do 3 times the work. Or if you lift just 1 bag 3 meters high instead of 1, you're applying that same force over a larger distance, which also triples the work.
And the math behind all this? It's beautifully simple. We measure force in newtons and displacement in meters. When you multiply them together, you get the standard unit of work, which is the joule. To put that into perspective, if you apply a constant force of 10 newtons to move an object exactly 1 meter in that same direction, boom, you've done exactly 10 joules of work. Moving on to Section 2, positive, negative, and zero. Because as it turns out, work isn't just a basic flat number. It can actually be positive, negative, or completely zero, depending on the direction of your forces. Just look at the visual contrast here. On the left, we've got someone pushing against a rigid brick wall. They might be grunting and sweating and totally exhausted, but mathematically, because the wall isn't moving, the displacement is zero. And since force multiplied by zero is literally always zero, scientifically, you are doing absolutely no work on that wall. Zero. Zilch. Meanwhile, when you actively move something in the same direction as your push, like carrying a box forward and letting it move with you, you are doing positive work. But wait, it gets even weirder, because work can actually be negative. Take a look at this goalkeeper diving to stop a moving football. The ball is displacing forward, right? Right toward the goal. But the goalkeeper's hands are applying a stopping force in the exact opposite direction of the ball's motion. Because the force and the displacement are essentially clashing head-on, the goalkeeper is actually doing negative work on the ball. They're essentially stealing its kinetic energy away.
Which brings us to Section 3, the work-energy theorem.
Think about your own physical exertion for just a second. Whether you're lifting heavy bags of wheat or trying to push a solid wall, ask yourself, if you're doing all this mechanical work, where does your ability to do it actually come from in the first place? And where does it go once the work is actually done? The answer is beautifully summarized by the work-energy theorem. This theorem tells us that the work done on an object is perfectly equal to the change in its energy. Honestly, work and energy are essentially just 2 sides of the exact same coin. That's why they're both measured in joules. When you do positive work on an object, it gains energy. For example, when a bowler throws a cricket ball, they're doing work on it, and that ball gains kinetic energy. When it smashes into the wickets, it transfers that energy, doing work on the wickets and sending them flying backward. It is a perfect mathematical exchange. All right, Section 4, forms of stored energy. Because mechanical work like lifting bags or throwing balls is really just one tiny piece of a much, much larger puzzle. You see, energy is like the ultimate shapeshifter. It transforms from one state to another without ever truly being lost. The food you eat, that contains chemical energy, which your body amazingly converts to power your muscles. The electrical energy in your home gets converted into light energy to brighten up a room, or thermal energy to boil your morning kettle. Even something as simple as a ringing bell is just converting mechanical energy into sound energy. And deep inside atoms, we have immense amounts of nuclear energy. It's just this massive, perfectly interconnected web of transformations. Now, when we zoom back in on strictly mechanical energy, it splits beautifully into two main categories: kinetic energy and potential energy. Kinetic energy is all about active motion. Think of a speeding car, or that kid zooming down the slide from earlier. Potential energy, on the other hand, is stored energy. You can store it by deforming something, like squishing a spring down, or by changing its relative position, like lifting a heavy object against gravity. When you hold a ball high up in the air, it's packed with gravitational potential energy. But the exact second you let it go, all that potential energy converts directly into kinetic energy as it accelerates toward the floor. Let's hit Section 5, the power of speed. So far, we've talked about force and distance, but adding time into our equations changes the whole game. Imagine carrying a super heavy backpack up a flight of stairs. If you trudge up slowly and it takes you, say, 5 minutes, you've done a certain amount of work. But if you sprint up those exact same stairs in just 1 minute, you are going to be completely winded. Scientifically speaking, because your weight and the height of the stairs didn't change at all, you did the exact same amount of work in both scenarios. Yet the effort feels completely different. So what's going on there? Well, that difference is power. Power is simply the rate at which work is done. You calculate it by taking the work done and dividing it by the time it took. So, doing the exact same amount of work in a much shorter time requires significantly more power, and we measure this in watts. The source material gives us a great example. If a weightlifter lifts a 75-kilogram mass by 2 meters in 5 seconds, she does 1,500 joules of work. But divide that 1,500 joules by just 5 seconds, and you see she requires 300 watts of power to complete that lift. Basically, the faster the work, the higher the power. And here's a fun little fact for you. You might already be familiar with another term for power, especially if you're into cars. Back in the early days, to help sell new steam engines, inventors needed a way to explain just how strong their machines were to a public that was mostly used to animal labor. So, they equated exactly 746 watts of power to 1 horsepower. They were literally comparing the output of their cutting-edge machines to the physical power of actual horses pulling heavy carriages. How wild is that? And finally, we arrive at Section 6, the dark energy mystery. We're zooming way out from lifting bags and climbing stairs for this one. We've spent this entire explainer discussing how energy transforms, right? From chemical to kinetic, from potential to thermal. But as scientists gaze up at the stars, they've realized that our universe's expansion isn't just happening, it's accelerating. And to explain this, they've identified a mysterious force called dark energy. But here is the massive catch. Unlike literally every other form of energy we've talked about today, dark energy cannot be exchanged. It just seems to create expansion out of absolute nothingness, sitting completely outside the rules of the work-energy theorem as we currently understand it. So I'm going to leave you with this final provocative thought. If this massive, unexchangeable force is actively accelerating the cosmos right now, basically breaking the very rules we just learned, how will dark energy govern the ultimate fate of everything, billions of years into our future? Something to think about. Thanks for exploring the physics of our daily lives and our universe with me. Keep questioning everything.